Today I also talk about one important topic of measure theory, which is Lebesgue Measurable Set. Okay, we will talk about this. We know about measurable set, but we also talk about Lebesgue Measurable Set. Let E be a set in R, then E is said to be Lebesgue Measurable Set if mu star A equal to mu star A intersection E plus mu star A intersection E complement for all A subset of R. Okay, now we're going to be some example of this, how this one is converted or how this one is handled. First we talk about Lebesgue measurable set, same as measurable set. Okay, but now we talk about some example. Okay, example, if that means if mu star of closed interval AB equal to what, equal to, we know about that, this one equal to B minus A, equal to obviously mu star of closed A open B equal to mu star of open A closed B equal to mu star of open A open B. Okay, in this way we also define this Lebesgue measure set. Okay, then we get this one. Now we talk about one important proposition about this Lebesgue measure set. Write this proposition now. Okay, let n equal to 1 to infinity be a sequence in R. Be a sequence in R. Okay, then what we get? Then mu of, okay, mu of n belongs to natural number set is equal to 0. How we prove this? This one is too easy. We done it, I think. Oh, here's some bastard version also gives bastardness here. Created one bastardness here. I don't know why they create this one, but now this one is okay. I start again. Okay, proposition, let an be a sequence in R, then mu of in this set n belongs to n equal to 0. Okay, how we prove it? Okay, now going to further proceed about it. Here an equal to, we talk about this sequence. Okay, then mu an equal to how much? Then mu an equal to 0, because this one is a singleton set. Okay, this one is a since a n b singleton set. Here just a n we write. Okay, mu a n equal to this one, then a n b singleton. Okay, some set notation, this one, then this one, a and b singleton element in a n. Okay, then what we get? We get here, since mu n is countably subadditive, is countably subadditive, then what we get? Then mu star of n belongs to this natural number equal to mu star of union of n equal to 1 to infinity an less than equal to summation n equal to 1 to infinity mu star of an equal to what? 0. Okay, so what we get? We get from here this one, mu star of this n belongs to this natural number equal to less than equal to 0. That means equal to 0. Okay, so we write here mu star of this set be 0. Okay, so we also prove this one. Okay, next we going to observation of something in this way that we write observation mu star of q equal to 0. Okay, mu star of q equal to 0. Then we're going to be discussion about some proposition. We also erase that portion and going to discussion about one proposition about that. Okay, now we write about this proposition. Yeah, let E be a set in R, be a set in R such that E be a set in R such that mu star of E equal to 0. Then E is Lebesgue measurable set. Okay, then what we discuss about today, E be Lebesgue measurable set. Then what? Then E be Lebesgue measurable set. We have to show that this one. Okay, so we are also going further discussion of that. We write here proof. Okay, we write proof of that. Then what we get here, let a subset of R, let a subset of R, then a intersection E subset of A. Okay, this implies that mu star A intersection E less than equal to mu star E equal to 0. Okay, then again we get here A intersection E complement subset of A. Okay, then this implies that mu star A intersection E complement, okay, less than equal to mu star A. Understand? Now we mark it 1. Since mu star be monotone, so we write this one. Again we talk about that A intersection E intersection A intersection E complement equal to 5. Okay, now we're going to since mu star be sub-additive, mu star be sub-additive, then what we get, then mu star A is equal to mu star A intersection E union A intersection E complement. Okay, this less than equal to mu star of A intersection E plus mu star of A intersection E complement. Okay, this marked as 2. Now from 1 and 2 we get, from 1 and 2 we get what? Here we write about that mu star A intersection E plus mu star A intersection E complement, obviously less than equal to mu star A less than equal to mu star A intersection E plus mu star A intersection E complement. Okay, then what we get here? Then we get mu star A equal to mu star A equal to mu star A intersection E plus mu star A intersection E complement. Okay, hence what that means, what conclusion we also arrive here? Hence EB measurable, Lebesgue measurable set. Okay, now we're also going further discussion of that. What observations we also now of that means, now we also arrived what observations here. If some subset of R and measure of this outer measure of this set or Lebesgue measure of this set equal to 0, then this set will Lebesgue measurable set. Also prove this one now, and further we also discuss about that one sequence in R, then measure of this sequence is obviously 0. We discuss this two result, and obviously discuss Lebesgue definition of Lebesgue measure set. Now we're going to be some observation of that. Okay, some observation about that we also going to now, then we also further proceed. Now we erase that portion and write this observation. I think all are understand this. Okay, easily understandable this one. Now we write here observation. Let an be a sequence in R. Let an be a sequence in R. Then first mu star of an equal to 0. An is Lebesgue measurable set. Okay, let an be a sequence in R, then mu star an equal to 0 and E equal to an is Lebesgue measurable set. Okay, now we write this proposition. Here. Let E be a set. Then for each epsilon greater than 0. Okay. Then for each epsilon greater than 0, there exists an open set G. With E subset subset of G such that mu star G less than mu star E plus epsilon. Okay, then what we get here? We write here proof. By definition of mu star E, by the definition of mu star E, we get, okay, mu star equal to what? Mu star E equal to infimum of summation n equal to 1 to infinity L of in, okay, where in is in I0 such that E subset of union of n equal to 1 to infinity in. Okay, then what we get here? Let epsilon greater than 0 be given. Let epsilon greater than 0 be given. Then there exists a disjoint sequence in. There exists a disjoint sequence in. Okay, there exists a disjoint sequence in I0 such that we erase our portion and going to forward discussion of that. There exists a disjoint sequence in I0 such that summation n equal to 1 to infinity L of in less than equal to mu star E plus epsilon. Okay, then what we get here? Will obviously define G equal to union of in equal to 1 to infinity in. Okay, define G equal to union of n equal to 1 to infinity in. Since G be open set, then this one is union of some intervals. Okay, since G be an open set, so it is union of some intervals. Possible? Then what we get here? Then we talk about that mu star of G equal to mu star of, okay, union of n equal to 1 to infinity in equal to summation of n equal to 1 to infinity mu star in. Okay, then what we get here? Then this one equal to mu star of C equal to n equal to 1 to infinity L of in. Okay, then what we write here? Then we write this one mu star G less than mu star E plus epsilon. Okay, so So we get our result. Then E be a set in R. Then for each epsilon greater than 0, there exists an open set G with E subset of G such that mu star G less than mu star E plus epsilon. Okay, I think all are understand this. Here not a problem at all. Then we also discuss about that some continuous function. Okay, we known about that. We known about some continuous functions. Okay, but today also some if G belongs to, that means if G is open set, then F inverse G is open, then F is continuous. We also known about that. Then today we also talk about this portion. Okay, some proposition related to this measurable set. Okay, some proposition related to this measurable set. We also erase that portion and going to discussion about that. Okay, now today we talk about this one, this proposition. Let E be a measurable set. Let E be a measurable set. Okay, then a measurable space X A in A be a measurable set in a measurable space, in a measurable space X A. Okay, then and if E to R, if E to R be a function, then the following are equivalent. Be a function, then the following are equivalent. Then the following are equivalent. Then the following are equivalent. First one, f is measurable. F is measurable. Second one, f inverse G is measurable set for all open set G in R. Each measurable set for all open set G in R. Okay, then also going to proof of that. Now we write here proof. If one implies two. How this one is then obtained? F is measurable, then F inverse G is measurable for all open set G in R. Okay, that means exactly as the same as continuity. Okay, if F is continuous, then F inverse G is continuous for all open set G. F inverse G is open here for all open set G in R. Here F is measurable, then F inverse G is measurable set. How this one is happen? Okay, we talk about it. Suppose that F is measurable. This one is measurable, we considered first. Then what happened? Then let G be an open set, G be an open set in R. Okay, we now show that F inverse G is measurable. Then we have to show that F inverse G be measurable. Okay, then how this one is happen? Since G is open, since G is open, then there exists a sequence. There exists a sequence here A N B N of disjoint open intervals disjoint open intervals in R such that G equal to union of n equal to 1 to infinity A n B n. Okay, then what happened? By definition, F inverse G equal to, here x belongs to E. Okay, such that fx belongs to G. Then what we get here? This implies x belongs to E such that fx belongs to union of n equal to 1 to infinity A n B n. Okay, then we erase our portions and going to further discussion of that. Then this equal to, here union of n equal to 1 to infinity. Okay, x belongs to E, fx belongs to A n B n. This equal to union of n equal to 1 to infinity, here x belongs to E such that A n less than fx less than B n. This equal to n equal to 1 to infinity, x belongs to E. Here x belongs to E, fx equal to greater than an, and intersection x belongs to E, fx less than Bn. Then this equal to union of n equal to 1 to infinity an intersection Bn. Okay, where an equal to x belongs to E such that fx greater than an and Bn equal to x belongs to E, fx less than Bn. Okay, understand? Then what we get here, also write in this way. Note that an and bn are measurable set for each n. Then that means AN intersection BN also measurable. Okay, since AN and BN are measurable sets, so AN intersection BN be measurable. Okay, then what happened? Then F inverse G equal to union of n equal to 1 to infinity Cn. This equal to write that union of n equal to 1 to infinity An intersection Bn. Okay, or Cn equal to An intersection Bn. Then this one equal to a countable union of measurable sets. Okay, a countable union of measurable sets. Okay, then this one equal to what? A countable union of measurable set equal to what? F inverse C be measurable. F inverse C be measurable. Okay, then next we go to this procedure 2 implies 1. Okay, we erase that portion and going to further discussion of that. Now suppose that F inverse G be measurable. F inverse G be measurable for all open sets G in R. For all open set G in R. Okay, then we have to show that F is measurable. F is measurable. Okay, how we show this one? First we let A belongs to R. Okay, then A belongs to R, then A plus infinity be an open set here. Then what we get by assumption F inverse of A plus infinity, okay, is measurable. Then what we get? Then F inverse of F infinity equal to x belongs to E, such that fx belongs to A plus infinity. Okay, this one be measurable. Then if x belongs to E, fx greater than E be measurable. Then this one equal to E, here A greater than E be measurable set. Okay, any problem here? I think not a problem at all. Okay, f inverse a infinity is measurable. This implies x belongs to E. If x belongs to A plus infinity is measurable, then E f greater than A be measurable. Okay, now we write about it. Since A be arbitrary, so what happened here? Easily we talk about that. It follows that. Okay, this E of A greater than A be measurable for all A belongs to R. Be measurable for all A belongs to R. Okay, then therefore the function f is measurable. The function f be measurable. Okay, so today we discuss about one important, that means proposition here. F is measurable, then f inverse G is measurable for all open sets G in R. Today we stop here.